my buddy lives here in South. It's actually like my really good friend's office. He's been there, he said, for 14 years.
Okay. All right. I'm going to get started because the semester is closing really fast, and I still have quite a few topics to go because the intention of this class is to give you the tools so that if you run into mysterious problems with your C or C++ program, you will have the tools and the knowledge to debug those programs. Where not knowing content of this class will be basically you will stop code and go like, okay, I don't know what to do now because I cannot explain the behavior of the program. Okay, so I do have to kind of go through all this stuff here, because that's the only reason why this class is even useful. Because most of you are not going to program in assembly, but most of you still need to program in C or C++, which means a lot of the topics that we are going to talk about from here on is even more applicable than the ones that we talked about earlier. But we cannot get here until we get all the other topics out of the way. But because we are running out of time, I'm going to have to change the order a little bit of how the topics are introduced. So what I'll do is I'll give you a homework assignment first. I have never done any homework assignment like this one. It's a really easy one once you understand the concept. So the whole idea of this homework assignment is the understanding of the concept. There's really no chore involved in this homework assignment. Okay, so the homework assignment is called link because we are going to link your, and we have link here. And this is an interesting program. Okay, this is an interesting problem. Sorry? Oh. And it's amazing how Zelda is still active. They keep coming up with new games. I think that's the only reason why Nintendo is not dead. That and Smash Bros. Wait, Link is in Smash Bros. In fact, there are 2 Links in Smash Bros. Yep, Zelda too. That's right. All right. So what I'll do is I'm going to, kind of give you an idea of what the program is for today or for this particular homework assignment. And okay. So here's the program. The program. This is the setup of the homework assignment. Once you untar this file, it will give you a folder, and inside the folder there are 3 individual files. They are all pretty small files. The one file that you probably don't need to mess around with is the make file itself. Oops. Oh, I have to change folder first. There we go. Okay, the make file itself, is something that you don't really have to do anything about because I set it up already so that all you have to do to create the executable is to type make. Make, press the enter key, it will do the rest for you. Okay? In case you think, I just messed up a whole bunch of stuff, I need to clean it up, say make clean, and that will clean it up. Okay, I will demonstrate. I will demonstrate what this means. Okay. Okay. So if you say make, it will figure out the dependency, and it will even show you all the commands involved. And in the end, it will give you an output file. In this case, the output file or the executable is called main, M-A-I-N. And you can GDB that main file. The compiler is already configured to give you the debug information, so you can use GDB on main and get it to work. Maybe not. I can see that one setting over here is not including that. I will have to retard and upload it again. I think it has to do with AS flags is -G. Okay, once again, if you want to clean it up, type make clean, and it will delete all the files that are generated. If you type make again, it will go ahead and it's still not doing that. I think the assembler option. No, it is. Okay, it is. It's working now. Okay, so now we can do a GDB on main, and you can list the file on the C side. You can also list the file on the assembly side. Okay. List, link, .s. It's not. It is not. It's uppercase S. Uppercase yes. Yes. It has to be that way. It's not including the dash G for. Let me try that again. Okay, so it is using dash G, so it should include that. No source file named link.s. That's not good. Okay, I have to get this fixed first because I need to make sure that you guys can debug your program. All right. Well, since I'm going through this, I might as well explain what a makefile is and also how to make changes to the makefile. Some of you may find this to be useful in some of your other classes as well, because this one is kind of useful. You can see that in this makefile, I have a whole bunch of stuff set up here. I defined the CC, the C compiler to be just GCC. C flags is what you specify in order to compile your C files into the object file. So whatever flag you specify here is whatever it will use when you compile your C files into the object files. You can add additional stuff to it. Okay, for this class, I would not recommend doing anything else because we're dealing with really simple files or simple programs. You can turn on optimization, like the dash O. You can specify dash uppercase O true or dash uppercase O 3 to turn on optimization. But for this class, dash O means do not do any optimization. Next line is AS flags or the assembler flags. Dash G should include the debug information. So maybe, just maybe, it needs G steps instead. I'll have to test this out. For your C++ classes, okay, if you're using C++, you will need to specify CXX flags for their C++ programs. All right, so let's try that again. Make, clean, make. Okay, this time it does use G steps as an option. Let me see if I can gdb main this time and put and list, at least be able to list link.uppercase S. Okay, all in one. It's still complaining no source file named link.s. All right, okay. I'm going to do it by hand first, just to make sure that it is the right step. ASG steps dash O link.o is S. GDB main. It's still complaining. I know it works, it's just that it does not want to get to the source file. Okay, I'll do this. Just give it a no ops here, and make clean, make gp main. Okay. All right. So I have to go through this step to show you what you guys have to do. You see on line 7, the printf is calling link. Okay, but this link is not defined as a C subroutine. It has to be defined as an assembly language subroutine that you have to write. So now we are trying to specify how to interface between C code and assembly code. Okay? So what I'll do is I'm going to single step through this and see if I can, get to that part. So put a breakpoint on line 7, run it, and then single step. So it is going to link.s. It's just that I cannot list that particular file from outside. So, well, that's okay. At least I am able to list that file at this point. So I can list link.s line 1, and now it works. So I guess I have to start to run the program first before I try to list the content of another file. Okay, well, okay, that crisis is done. Okay. Okay, but the key is now, how do we specify, how do we interface C code to assembly code? Okay. Now, the reason why we want to learn that is because, once we understand how a C subroutine gets its parameter and its local variables and then how it treats pointers, now we will be able to understand what you can do to corrupt the stack, and for each type of corruption, what would be the symptom that you'll be able to see when you run your regular C program. That is the objective of what we are talking about here. Because I know most of you are not going to write subroutines in assembly. Okay, most of you will stick with C or C++. But most of you will also end up corrupting the stack at one point or another. So I want you guys to understand what it means to be corrupting the stack, what you can corrupt on the stack, and how your program will behave when you corrupt the stack. So those are the objectives. All right. So getting back to link here, okay, main is easy. Main.c doesn't really do a whole lot. Okay, we have seen that already. This is the main program. There's nothing, absolutely nothing that you have to do to this particular code. Okay, all it does is to call link with a parameter of 10, and then it prints out the return value of link. That is all that it's going to do. Are there any questions about the main program itself? Yep.
On the prototype, what does extern use? What does to link with the assembly?
The extern on line 4, basically,
Yeah.
the extern is the same thing as a .global in our assembly file. All it's doing is telling the C compiler and also the linker and say somebody is going to define this label link, the subroutine link. But it's also defining the return type of link as well as the type of its parameter. But it is just telling the compiler, it's okay if this subroutine is not defined in this file, because somebody else may be defining it. So it serves the same purpose as .global, except there's type information in this case. Are there any questions? Any other questions about this file? No questions? Okay. Now, if there are no questions about this one, we'll switch to the other file. The other file is link.s. Okay, link.uppercase s. The first part, the first 4 lines, you can see they are quote unquote double commented out, using 2 pound signs. From now on, we'll have to do that because once we use pound include in our assembly source files, we'll have to use 2 pound signs to escape or to use comments. So in this case, this is what you're implementing. You are trying to implement a C subroutine, and all it does is to take an integer parameter, double it as the return value. That's all. Okay, but you want to do it in assembly. So the difficult part is not how to add a number to itself. The difficult part is 1, where do I find the parameter? And 2, how do I specify the return value? Are we doing okay so far with that? With the homework assignment, what you have to do. Is that okay? So the question is, how do we do this? I mean, we have never seen anything like this before. How do we do this? Now, without taking this class, if I just tell you one thing, if I tell you that the parameter is on the stack, okay? If that's all I'm going to tell you, what are you going to do to investigate how to get this homework assignment done?
How to manipulate the stack.
Hmm?
How to manipulate the stack.
how to manipulate the stack, or in GDB, how do we take a look at the stack? Okay, sorry?
Do you like IRESP to see where it's
IRESP to find out what the stack point is pointing at, and then after that you can use the X command to do a dump, and then you can try to identify and go like, okay, I know I just pushed this kind of unique value on the stack, where is it now? Okay, so what we'll do is we'll take a look at the stack first, and say, at least be able to see that the parameter is actually on the stack, and then we'll try to explain what are the other stuff on the stack when you get control in your subroutine. Okay. All right. So instead of doing your homework assignment, I'm going to copy this to something else. So I will copy -r link to example 1. So now I go to here, and I'll give myself a slightly different homework assignment. Okay, different assignment, and I'll just say, function f. But this time I'll give it a particular bit pattern, a 32-bit bit pattern that is unique. So this way I can easily identify and say, oh, that's the parameter. I just, this is what we want to find. Okay, so we'll make this kind of somewhat unique. A, B, C, D, 1, 2, 3, 4 is probably fairly unique as a 32-bit number. And we'll change all the other stuff too to kind of match this. So instead of using a subroutine that returns a value, we'll just say it does not return anything, but it does take one parameter. Okay, that's the first thing we do. And then I'm going to change the name of the assembly file from link to f.s. You don't have to do it this way, but it is just my personal preference to make the source file to implement a subroutine the same name as the subroutine itself. Okay? So you don't have to do this, but I think it is a good idea. So in f.s, I'm going to have to change the label, the entry point to just f. I also have to change .global to .global f, because remember, .global is the same thing as extern. It is telling the assembler somebody else may be interested in this symbol f. Export it so that the linker can see it. But it makes sense because the C program wants to call f, okay? But f is not defined in main.c. So the linker now needs to say, okay, main wants to call f, and who is defining f? Oh, I can see that f.s is defining the label f. So the linker can do its trick and resolve the unresolved references. Are we doing okay so far in terms of the concept? Why we need a .global f in this case? Is that okay? All right. And because f is a subroutine, I better have a return at the end here. Okay, because as any subroutine, if you have a caller, you need to be able to return. So I will specify a return statement here. And other than that, I'm not going to do anything. Okay, this is all that I'm going to do. And the last thing I have to do is to change the makefile. And when I change the makefile, the only part I have to change here is to change the source code. Instead of link.s, I change it to f.s. There's nothing else I need to modify in this makefile because everything else only rely on these variable names. So all I have to do is to change the variable definitions, and the rest of the file can remain exactly the same. How many people are starting to use makefiles in your other classes? And are you guys running into kind of like tedious stuff of maintaining the makefile because you have pound includes of your own definitions? This can take care of all of that stuff. Okay, we will take care of those later on, but right now we'll focus on the homework assignment. Okay. So I say make clean. There's nothing to clean because I don't really have anything created yet at this point, and I just say make, and everything is done already. So I use GDB main, and I try to use the debugger to help me figure out what is on the stack. So I will put a breakpoint on subroutine f or the label f. That's perfectly okay. Run the program all the way until I get to the entry point of the subroutine f. So right now I'm just about to execute the first instruction in the subroutine f. And what did I want to do again? What was the whole purpose of going through GDB?
Look at the step.
To try to figure out where on the stack is my parameter, right? Okay, so let's go ahead and take a look at ESP. technically speaking, I don't even need to know what ESP is because I can refer to $ESP in the examine the X command. But it doesn't hurt to kind of take a look at this one. And then what I'll do is I'm going to examine the memory content. So I'm going to examine, let's say, a bunch of items, okay, maybe 8 items. Each one is a 32-bit it's a 32-bit quantity. I want to print everything as in hexadecimal because the ABCD 1, 2, 3, 4 is in hexadecimal. So I want to keep my display, the formatting in hexadecimal as well. And we'll go ahead and use whatever the stack pointer points to as my starting point of the dump. The reason why I use my stack pointer as my starting point is because the stack starts high, and as you push items, it goes lower and lower. And the stack pointer is always pointing to the lowest byte of the last item that we push on the stack. So this is the entry point. This is actually, you know, the beginning part of the stack that contains something that is meaningful to me. Okay. So I will press enter and take a look at this content here. Okay. Do you see ABCD 1, 2, 3, 4 here? Definitely. Okay. That's good to know. But it's not the first item. In other words, there's something else on the stack. Why do you think there's something else on the stack?
The call to the function, or the call to the label F, like the pointer to F, basically.
It's the return address.
The return address.
Because when you call
to F.
Yep, exactly. You also have a return address. So that's why we have the 0x 080483E2. That's what it is. That's the return address.
Is that where your is that where your stack pointer is?
No. Well, yes, the stack pointer is pointing to that location right now. So if I were to execute a return statement right now, it will return to the right place. It won't make use of the parameter at all.
But if you were to pop off the stack right now, would you get a seg fault because you're popping
The pop would not do a seg fault, but by the time I get to the return, it will do a seg fault.
Right.
Because it will attempt to return to the location ABCD 1, 2, 3, 4, which is out of my range of addresses that I can access. Right? Cool. So we can, in fact, find the parameter on the stack, and we can also explain what the other byte or what the other word is, 32-bit word. That's our return address. Are we doing okay so far with this homework assignment? Yep.
Why does it have a return address when it's a void function?
A void function means it does not have anything to return as a return value. But the return address is still needed by the return instruction to continue execution after the subroutine is done. So you got to make sure that we differentiate between the return value as opposed to the return address. The return address is not explicit when you are coding in C and C++, and that's why most of the time you don't even talk about it because it's not visible, it's not really usable from a C and C++ perspective.
Is there a call address too before our parameter? Is that the call? Is a call address pushed onto the stack also?
The call address.
Like when you make a call, does that get pushed on the stack?
No, when you do a call, it has two things to do. The first thing it does is to save the return address, push the return address on the stack. And then the second thing it does is to just jump to the entry point of the subroutine itself. So the address of the subroutine is not on the stack. You just kind of jump to that location. Okay.
So where it would return, if you have return value,
Say again?
if you have return value, where it have space for it.
Well, we'll do it in a separate example because I will give you the pieces and then you guys can put it together. Okay. All right. So now that we know, there's the parameter on the stack and there's the return address, I'm going to stop this particular sample program right here, just so that you know the parameter is on the stack and it has a location that is above the return address. Okay. So what I'll do next.
Chat.
Yes. Yep.
So ESP is pointing to the 4 and ABCD 1, 2, 3, 4.
No, ESP is not pointing to the parameter. It is pointing to the return address.
So it's pointing to that 2, the lowest.
is pointing to 0x080483E2. It's pointing to the return address. Because the call instruction is the last instruction executed. So that also means that the pushing of the parameter is the first thing to do, and then the call happens after that. Okay. So are there any questions about what the stack looks like at this point, and at least be able to explain the two 32-bit things that are on the stack right now pointed to by the stack pointer? Okay. All right. So when this is done, I'm going to move on, and we'll do something else. Okay. So here's the second example. Okay. So I'm going to copy again EX1 to EX2. So in EX2, I'm going to change main a little bit. Okay. So in this one, I'm going to specify that f would return. Well, let's not use f here. I'm going to change the name of f to 81. Okay. And this subroutine does not take any parameter, so the parameter is going to be just void here. And then what I want to do is to use printf and say 81 returns, and then we try to print out what is returning. So we'll make a call to 81 right here and print out its value. And for those of you who are used to C++ but not C, this is the same thing as cout less than 81 returns blah blah blah, and then less than, and then 81 the call to the subroutine. Okay. All it does is to print out the value that is returned by 81.
You made value on the board?
Cout 81 returns space double quote less than 81 function. Same thing, except it's using printf.
It's a function, right?
Huh?
81 is a function?
It's a function call. Yeah. Okay, because the whole idea of this homework assignment is to understand from the callee's perspective, how do I get to the parameters and how do I specify a return value? Are we still doing okay at this point? Okay. So now I have to go to my makefile because I have to change, whoops, and then change my file, f.s. Oh, there's only one file. This is the nice thing about doing it this way, because there's only one reference to the assembly language file, so there's only one thing to change. 81 is the name of the file, and I have to move f.uppercase s to 81 uppercase s, and then change everything here. Change f to 81. Okay. All right. So the question is, how do we return 81? Doesn't take any parameters. So this time I don't have to look at the stack and find out what the parameters are passed to me, because I'm not expecting anything. So the question is, how do I pass something back to the caller? Now, some of you are thinking the stack, and you are partially correct. There are times when the stack is used to return a value. Okay, but that is only happening when you're returning a structure, not a scalar. An integer, a float, a char, a pointer, those are all called scalars because they are fairly small and they can fit inside the register. Any structure that you want to return cannot fit into a register, and you will have to use the stack as a mechanism to return a structure. But this is just an integer, so it will fit into a register, and the register that we use to return a 32-bit value, guess which one it is? EAX, exactly. So if EAX is the register to store the return value, how do I return 81 as a value? I just copy the constant 81 into EAX. That's all I need to do, right? Well, just because I say that doesn't mean that it is necessarily true. So we'll go ahead and make, and then we'll run this program. Now this program doesn't even need to be run through GDB because there's output, it should print 81 in this case. But I'm going to go through GDB also, just so that we know that we are in fact calling the assembly subroutine from C and then coming back to the C subroutine. Okay. So we'll say GDB main. We'll put a breakpoint on 81. Do a run. Okay, so now we are in the only instruction inside 81, which is to move 81 with a $ immediate into EAX. Okay, single step. Okay, if you want to double check, okay, that's the result. Not very surprising, not very exciting. Okay, we just copy the value 81 into EAX. Sorry.
Oh, it's extremely exciting.
It is kind of exciting in a way. Okay, and then we go back to printf, and then we continue execution. Okay, this is going to take a while. I'm going to have to I'll just go ahead and continue execution. And it does go through the entire subroutine. This is the output of the entire program. It says 81 returns 81. Okay, so now we have the two pieces that you need in order to do your homework assignment. But I have not given you the third piece, which is what is the best way to do it. Okay? I'm pretty sure some of you already know, have a certain way to do it, because once you know where it is on the stack, you can probably, like pop twice, get to that one, and then push something back onto the stack, just so they don't disturb the order of stuff. But there are better ways to do it. Okay. So what I'll do next is to show you another sample program that can also be a piece of your homework assignment. So we'll do a cp-r ECX2 to EX3 in this case. Okay. All right. So this time we'll take a look at main.c again. We'll change the subroutine to void, and we'll just say many params. Okay. In other words, many params is the name of a subroutine that takes on multiple parameters. Because if I'm putting all the parameters on the stack, what is the ordering of those parameters? Which one comes first? Which one comes next? Which one has a lower address? Which one has a higher address? I want to know that.
Oh no, I thought you were asking.
Okay. So what we'll do is we'll do the same trick as before. We'll have 1, 2, 3, 4, A, B, C, D as the first parameter. Whoops. This is the prototype, so I cannot do it just yet. So in 32 underscore T, in 32 underscore T, it will take 2 parameters. I don't need the printf here. I just need many params. This time 1, 2, 3, 4, A, B, C, D as the first one, and then the other one can be C, D, C, D, E, F, and 9, 8, 7, 6. Okay, there we go. So these 2 patterns should really stand out, and I should be able to identify both of these. So the question is, which one has a higher address and which one has a lower address? Because eventually, if you want to understand how this works, you also want to understand how are the parameters pushed on the stack. Are there any questions about what we are trying to do here? We're trying to figure out the ordering of the parameters on the stack. Okay. So let's go ahead and take a look, and we'll change the makefile first. So instead of 81, now we have many params. And then I'll just go ahead and move f.c, f.uppercase s to many params.uppercase s. It's not here because I changed that name already to 81. There we go. Oops. 81. Oh, 8181. There we go. Too many params. There we go. All right. I don't really need the no-op instruction. Just a return instruction is fine, because my only purpose is to figure out the ordering of the parameters on the stack. Okay, this has nothing to do. Okay, the subroutine really has nothing to do. All right, so we'll go ahead and do a make. And I had a syntax error in main.c on line 6. Oh, semicolon. But it never complains that I'm missing a semicolon. It gives you all kinds of error messages except you're missing a semicolon. Or did it actually mention a semicolon? Nope, did not mention it.
Expected up there, but it doesn't tell you which one.
Expected over.
It doesn't narrow it down for you.
Did it?
Right there.
Well, it said expecting, a few things.
Something should be there.
Yep. That's okay. I used to write compilers, so I can really understand from the compiler's perspective why it cannot really give you a good clue of what happened or what the mistake is. All right. So we'll go ahead and GDB main and put a breakpoint on many params. I just used the tab key to auto complete. Yep.
Is it okay if we edit the make file?
Sorry.
Is it okay if we edit the make file?
Is it okay to what?
I'm adding it. Can I add additional flags to the make file?
Absolutely. Go ahead. All right. So I'm putting a breakpoint at the entry point of the subroutine. Run the program. Now we are on inside the subroutine itself. We'll do exactly the same X command here. I will display 8 items. Each item is 32-bit in hexadecimal, starting at wherever the ESP is pointing to. And do we see the order? We definitely see the order here.
2 and 3.
The first parameter has a lower address, and then the second parameter is next to it. Okay, but in terms of push operations, which one has to be pushed first?
Higher one.
The
Second parameter.
Second parameter.
Yep, exactly. So in general, in C, the last parameter is pushed first, and then the first parameter is pushed last. Okay? But that is really backwards. The first parameter should be pushed first. So what is the whole idea and the purpose of pushing parameters in the backward order?
Popping them, but
Put the
Hmm?
it's easy to pop them.
It's easy to
Pop.
pop. Say again? Pop. Pop? No, we don't even need to pop the parameters. We can just move the stack pointer. The reason why it is pushed backwards is because in C and C++, you can have a variable number of parameters to a subroutine. I'll say that again. Because from the reaction, I think, I'll say that again and then I'll explain what it is. In C and C++, you can define subroutines that can accept a variable number of parameters. Not 1, not 2, but you can specify as many as you want. Yep. Not overloaded. This is regular C, it's not using C++ overloading at all. Okay, so I'm going to give you one example of what it looks like, and then we'll continue on to the main topic here. Okay. So what I can do is I can modify this one, many params. Oh, I can modify main here. So instead of saying that it has 2 parameters, I can do this. ... Now, once you specify ... it means the first parameter is required. But after the first parameter, it can have as many parameters as it wants after that. Okay? Yep.
But they will all be like integer type?
No, it can be of any type. You can have chart pointers, void pointers, floats, doubles. Doesn't matter.
And they will all be shown in the function when it's called? They will all be shown in the call?
They will all be accessible once you locate the address of the first parameter. Then you can use that to get to the other parameters. That is the reason why parameters are pushed backwards, while last parameter is pushed first. Because this way, the first parameter has the lowest address. And once you get the address of the first parameter and the size of the first parameter, now you know the address of the second one. And if you know what to expect in the second one, you can also get to the third one, the fourth one, and so on. Okay. Very few people write subroutines this way anymore. I think with C++, there are other ways to handle situations where you need to pass a variable number of stuff to a particular subroutine. But in the good old days, this is still the way to do it. And it is still supported today by C++. So you can still write subroutines like this, so you can pass any number of parameters. Printf is a really good example. You can pass any number of parameters. Yep.
But if you pass any number of parameters in C++, when you go to call the function and you pass in, say, a char, and you haven't designated what it can take in, it just knows, it'll cast it?
No, it does not. So what you need to do is your subroutine needs to know what it is expecting.
Right, but when you're, so how would you write that out in like a C++?
In C and C++, in the same way.
If you have a variable number of parameters being passed in.
Okay, so in this case, I'm gonna put this all inside a block of if 0. This is a quick and easy way to comment out a block of code. Because anything within a pound if 0 and a pound end if is just ignored by the C compiler, because the preprocessor will basically just cut out all this stuff before it feeds it to the C compiler. So in this case, if I want to write this particular subroutine in C, I can do it like this. Okay, many params in32 underscore t first param and dot 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 comma dot dot dot. Okay, so what I need to do in here is a void pointer. Okay, so the void pointer serves a purpose, because the first thing I would do is the void pointer gets the first parameter. Is that okay?
Yeah.
And then what I would do so when it is time to get to the second parameter, okay, fine, comment. Okay, so when it's time to get to the second parameter, what I would do is I would do something like this. So I would do a ptr gets cast in 32 underscore t pointer ptr, and then do a plus plus here. Well, you can do a post increment of the, nope, I take it back. This will increment ptr to point to the next available parameter. Now, what is the type of the second parameter? I cannot tell you. Okay, there's no information about the type of the second parameter. I just know where it starts. Yep.
How does it know how many parameters pass it? So where is stored in the stack?
What is stored on the stack?
Where is stored in the stack?
You don't know. That's a very good question. The question was, if I handle a variable number of parameters like this, how do I know where to stop on the stack? The answer is I do not. It is all based on the first parameter. So typically the first few parameters will give you a clue of how many you should expect, which does not mean that many is actually provided to you. And that can cause problems, obviously. So that's why this method of doing things is not really done much more these days, because it does open up a lot of security holes. But that's the reason why parameters are pushed backwards. Or this is why the first parameter needs to have the lowest address, so that you can get to the other parameters through the first one. All right. So are there any questions about this part? This is the C code part. I'm not going to ask you anything about. I just want to explain why parameters are pushed backwards. The last parameter has the highest address. The first parameter has the lowest address. Okay, are we still doing okay so far? Okay. Third piece of information that you might find useful for this homework assignment, even though most people probably would not use it, is the addressing mode. Okay, so let me see how I'm gonna do this. Okay, we can do it this way. So in this case, we have many params dot uppercase s. All right, so let's say I want to do some calculations here. Let's say I just want to check whether the second parameter is 0 or not. Okay, that's all I'm gonna do. So I can do a single compare instruction, compare long, because I know both parameters are 32-bit. $0 as a constant to compare to. Now the question is, how do I get to that parameter without having to pop and then re-push stuff and moving things around a lot? Yep. Say again?
DBAS one.
Yep, using the addressing mode to help me. Okay, very good. Okay, that's a very good starting point. The starting point is to understand that the Intel architecture is a cisp architecture, so we can do a lot of stuff with the operands to do some of the calculations for us. Okay, D, B, this is I, this is S. Okay, this is the most general form. But in this case, we know that we are accessing something that is at a certain offset from where the stack pointer points to. Okay, so that means the fixed offset can be this component because it doesn't change. It is always 4 bytes after or 8 bytes after. The second thing we also know is the B. Which one should be my base register?
ESP.
ESP, exactly. So what we can do here is to say, well, we know that second parameter is always at 8 bytes away from where the stack point is pointing to. That's it. I can now check whether the second parameter is 0 or not in a single instruction. Are we still doing okay so far with this code? Yep.
Increase the font size, please.
Increase font size. View, edit, preferences, appearance. This is pretty much as big as I can get without. Is that okay?
Yep.
Okay. So this is why we have to study the various addressing modes, to begin with, because now the base addressing mode becomes very handy. Because if I know where the stack pointer points to, I know where to find my parameters. Okay. Are there any questions about this portion? Yep.
So you couldn't have a negative there, right? Or could you?
Oh, you can have negative. In fact, later on we'll have negative.
Okay.
Yep.
So if you do 8, it's gonna go which direction on the stack? Towards the first in?
It goes up. It's because the effective address is 8 plus whatever ESP has.
Right.
So you are going. The stack pointer right now is pointing to the return address.
Right.
And then after the return address is the first parameter, and then after the first parameter is my second parameter. So this is actually checking whether the second parameter is 0 or not.
So what was pushed on, when you do 8 ESP, my question is you're going what was pushed first. You're going towards what was pushed first when you do 8. Right?
It's basically just 8 bytes away from where the stack pointer points to.
Right.
Because
But there's that's 2 directions. You can either go left or right. So I'm saying it's going more towards what was pushed in first.
Yeah.
Right.
Mm-hmm.
Okay.
This is what is pushed first.
And if you were to do -8, it would go back the other direction, like
Now -8 is going to land you somewhere that we have not pushed anything yet.
Right.
Because remember, the stack pointer points to the lowest byte of the last item that you pushed. So anywhere below that point, if you specify
Nothing
anything
pushed on
negative,
there.
the memory content is still there, but we don't know what it is because we have not pushed anything yet into that space. Because the stack pointer points to the boundary right between the portion of the stack that has content that you pushed versus the content of the stack that is unused at this point, uninitialized, unused. All right. So how do we know this works? Well, let's see how we can check it.
So we ask TAC to prove it.
Yep. But the way I prove it, and the tricky part is how do I prove this without giving you too much information of how to do your own homework assignment. I can do this. In other words, I intentionally make the second parameter 0, and then I can set up a breakpoint inside the subroutine and check the flags and see if it is 0. Does that make any sense? Okay. This is a very roundabout way to show you guys how to do your homework assignment because I don't want to hand it to you. But you will be able to see it, okay? I think some of you are already making connections here. Okay, make gdb main. I put a breakpoint in the subroutine itself, many params, and I run the program until I get to the breakpoint here. First thing first, okay? I still want to double check that the several items on the stack This time I know I only have to dump 3 items from the stack pointer because the first item where the stack pointer points to is the return address. Right after that is my first parameter, and then right after that is my second parameter, which is supposed to be 0. Okay, so I want to confirm that. So I'm going to dump 3 items. Each one is a 32-bit thing. I want to print everything in hexadecimal, starting with whatever the stack pointer is pointing at, and that's exactly what we're seeing. Okay, just as predicted. The first item is the return address. The second item is the first parameter, and then the third item is my second parameter, which is 0. Okay, so now I'm going to single step through the compare instruction. Single step. And after the compare instruction, which is comparing 0 to 0. Okay, so at this point, the Z flag should be on, it should be set. So I do an IRE flags. And sure enough, the Z flag is present. Okay, I don't really care about the other flags, but the Z flag, the 0 flag, is definitely on, which means that I am comparing the right thing. Okay. If I can compare the second parameter to a constant of 0, can you double the value of the first parameter and put it into EAX? So you have to kind of make the connection between the several sample programs here. Okay, the first one shows you where the first parameter is. The second one shows you how to return a value. And then the third one, which is this one here, shows you a particular addressing mode that you can use to access a particular parameter or anything on the stack relative to the stack pointer. So when you combine these 3 concepts in a week of time, you should be able to get your homework assignment done. Are we doing okay so far in terms of the concepts? How about the commands that you can use in order to look at the content on the stack? Okay, the X command is useful. Examining the stack pointer is going to be useful. Okay. How do you test your program? Yep. So this is your homework assignment. Okay, you have 1 week to do it. Let me count the instructions that you actually need to specify in the subroutine. 2 instructions, maybe 3, including the return instructions. Okay, that's it. So you do have to kind of think about what we have just talked about, and think about how each piece, each sample program, relates to your homework assignment. I will make the 3 sample programs available to you, so you don't have to worry about, okay, did I copy the right thing? I will make those available. Okay. Are there any questions now at this point about the homework assignment? Yep.
So we're going to change the C code to assembly code, and we're going to have our link file to be assembly code also, basically.
Yeah, link.s has to be in assembly.
They're both going to be assembly, or no?
Which one? Main is always in C, and then link is the only one that needs to be specified in assembly.
And we're going to be just editing link.s.
We'll just be editing link.s. That is correct. That's the only thing you have to edit, and then make will take care of the linking and the.
So the C code is basically what we want.
The C code is just sitting there. That's your. It's basically for testing purposes. Just to make sure that your code can work with C code. Yep.
So, if you want to test our program, you can pass a value to our program, and the program should return that value, or?
Right. The way I will test your program is not to run it and see if the output is 20. The way I test your program is I will set up a breakpoint inside main, and then I will just call F or call the subroutine directly, and then check its return value. So this way I can, once again, use multiple test cases to see if it returns the correct value. Any other questions?
When can we turn in?
When?
Yeah.
From now to a week from today. Yep.
When we need to return something bigger than EAX, I don't know, return like array or not array, something.
A structure. If you
Yes,
need to return a structure, then you need to use the stack to do it. That's somewhat complex, so we will talk about that later. Okay, but C and C++ has the ability to return a structure to the call. Okay, most of you probably have not done it. You'll return a structure in C and C++, but you can. There's the ability to do it. All right.
So I just would like to clarify, so a return value stored in EAX?
Right, any scalar that fits in 32-bit is going to be returned in EAX. So it can be a pointer with a 32-bit system, can be a 32-bit integer, can be a float, because a float is by default 32-bit. So all of those will be returned in a single register EAX. At least in a 32-bit environment. With a 64-bit environment, they probably use the 64-bit of EAX as the return register. Yep.
In 64-bit, you can pass, you can change the add flags for the loader and the assembler so that it compiles everything, and or the C compiler, so it does it all in 32-bit.
Okay.
So you don't have to change anything.
I see. Cool. All right. So this is now that this is out of the way, we'll move on to some topic that is kind of related to this, but it's not something that you need to use in your homework assignment. Okay? Okay, so let me point out one limitation of this approach here. So I'm going to go back to here. Okay, so it is unlikely that your subroutine is always going to be this simple. Okay, so there will be cases where you use up all the registers for intermediate results, and you still run out of space. So what do you do when you have used up all the registers and you still need some more stuff or some more storage to store intermediate computation results? Well, you can use the stack, right? So that's a pretty kind of standard way to do things. So occasionally, before you perform a certain operation, you might want to say, oh, I need to push a register because I need to use that register, and I need to preserve its existing value, but I need to use it again now. Okay, then you will pop it later on. Okay, but this is really bad for this code. Why do you think this code is not going to work anymore at this point? The push and the pop do not seem to have any effect, right? I mean, if I push EAX and then pop EAX, then EAX is not changed, okay? Because I'm pushing and popping exactly the same thing. So why do you think that will make this program incorrect at this point? Yeah?
The stack pointer changed.
The stack pointer has changed. So that 8 should now be 12 because I have just pushed or decrement the stack pointer 4 more bytes. So now it will be 12 bytes away from the first parameter, from the second parameter. Okay. So the question now is, well, I can go back and adjust that 8 to 12 to fix this problem, right? I mean, easy enough. Okay. So as long as I can keep track of how many stuff or how much stuff I have pushed on the stack and popped on the stack, I can keep changing that offset. But it's tedious. Okay, this is very tedious, and if I forget about one particular push and one particular pop, my entire subroutine may not work anymore. Yep.
But can you just use move instructions?
The move instruction to move on to what?
You can like move whatever you want to, like if you know the location of the value that you want on the stack, then you can move that value using indexing, using base index.
But where am I moving it to?
You can move it to a register that's the width and the size that you need.
But I have used up all the registers already. That's the whole point. Is after I use up all the registers, and I still need more space to store a temporary result from some calculation, then I have to use the push instruction to say, okay, save that register. I need to use it later on, but now I need to use it for something else. And then after that something else, I will pop it back and say, okay, now I need to restore the original value of that register so I can continue with whatever I left off earlier.
Can you pop it back onto the stack?
You cannot, okay, it doesn't make any sense to pop it on the stack.
Sorry.
Because when you pop, you're removing something from the stack, but when you say pop it back onto the stack, then you're not doing anything, right? So you cannot pop something on the stack. So the bottom line is, something like this is bound to happen when you have complex, logic to deal with. The the main point is I don't want to have to keep adjusting that offset. Okay, because if I have another push, let's say what I'm doing here is really, really complex, and I need to have another register here. Let's say I have the use of EBX. I can always, just make sure that I push and pop in the right order. So as far as EAX and EBX are concerned, they are restored, they are saved and restored correctly, no problem. But as far as the offset is concerned, now I have to adjust to the 16 because I have just used up another 4 bytes on the stack. So the distance from the stack pointer to the second parameter is now 16 bytes and not the original 8. Yep.
A push W would mean you'd have to increase it by 2 to do a push W?
Yeah, push W would only increase it by 2. Okay, so I don't want to have to deal with this. Okay, in other words, I don't want to have to keep track of all the push and the pops so that I keep adjusting that offset all day long. And this is why we need to introduce another register. It's called EBP. EBP is called a frame pointer. Okay, so let me just kind of restore this file back to the original state so that when I archive this and push it on Moodle, it will be correct. So I'm not gonna touch this file anymore, and we'll go ahead and copy this to EX4. Now remember, EX4 is not something that you have to do for this particular homework assignment, but eventually you will have to do it this way. Yep.
This is useful when you have to use up all the registers.
Yeah, this is useful when you have to use up all the registers, but it also serves a second purpose. It allows you to traverse the stack and find out, oh, I got to this subroutine because this subroutine called me, and it can go all the way back to the first subroutine that called everything, like the main subroutine. So we're going to talk about this in EX4. So in EX4, I'm going to use the same subroutine, which is main.manyparams.s. But this time, what I'll do is I'm going to do it in a much more systematic way. I just realized that I forgot to do one thing, to fix one thing to make the previous program work again, which is to change the offset back to 8. See, this is a prime example of the trouble with this particular approach. When I delete the push and the pop instructions, I have to go back and change the offset back to the original, okay? Which is really troublesome because if you forget to do that, your program is going to access the wrong part of the stack and you won't be accessing the parameter that you want to access anymore. Okay. So getting back to this particular file, we'll go ahead and change this a little bit. So what I'll do is I'm going to, well, first of all, I remove the comments here, and we'll change the main program also. So we'll change main, back to only using 2 parameters. 32T. Which really doesn't affect anything from this perspective. But what I'll do here is I'm going to define some labels, okay? And also what I'll do is I'm going to introduce another register called EBP. Now the thing about EBP is the first thing I do is to push EBP on the stack, and then right before I return, I pop EBP from the stack. Okay, well that's fine. Big deal. Having a push at the beginning and a matching pop at the end means EBP's value is preserved. From the caller's perspective, EBP has never changed. So that means between the line of push L EBP and the line of pop L EBP, I can do whatever I want with EBP and the caller would not be able to know. Okay, is that okay so far? So the next question is, what am I going to do with EBP? Well, it's called a frame pointer. And as a frame pointer, the first thing I do to it, and the only thing I do to it, is to say move ESP to EBP. In other words, I just make a copy of ESP and say, hey, EBP, I want you to be a copy of ESP at this point of time in the subroutine. Am I doing okay so far with this code? Okay, well that's not too bad. Now how do I, designate the offset to the second parameter? Let me save this first, and going back to the main file, the C file, in the prototype, I'm going to name the parameters so that we can match the parameter in C to the parameters in assembly. So I'll just call this parameter X, and I'll call the second parameter y. Is that okay? In the previous version, I did not name the parameters in the prototype. I just now give them names. Okay. Now I go back to the assembly code, and I want to calculate the offset now. Okay. Use EBP as a reference point from here on. Okay. All right. So that means I want to define some labels to say that, okay, at this offset from where EBP points to is this item on the stack. Okay. What is the stack? What is the frame pointer pointing to right at this point? Right at the point of this line of comment.
Same place that ESP is pointing.
It is exactly. It is pointing to the same place where ESP is pointing to, but what is the content at that location? What is ESP pointing to right now?
Return address.
No, it's not a return address because it's pointing to the last thing that was pushed on the stack. What did we push on the stack?
Oh,
EBP, right?
So it's pointing to
So
itself.
it's pointing, well, not exactly itself, it's pointing to its former self. Because we did change it with the move instruction after we pushed it. Okay? So but EBP is pointing to its former value. Is the value before we changed it. Is that okay? So what I'm going to do is I will use some labels to define, what is the content at various offsets from where EBP points to. Not ESP anymore, just EBP. Okay. So we'll say old EBP, which is the previous value of EBP, is at an offset of 0 from where EBP points to. Is that okay? This line is just a label definition. It simply tells the assembler every time you see old EBP, it's the same thing as seeing 0. That's all. Okay, it's the same thing as in C and C++. How define old EBP 0? Okay, there's no difference between those two concepts. And then the next thing is what is on top of that. Okay, in other words, if I want to describe what is at a displacement of 4 from where EBP points to, what is that? The address of is the return address. Okay, so the return address is 4 bytes away from where EBP points to. Return address. I just use a label for that. But instead of doing it this way, I'm going to say it is old EBP plus 4. So this way, everything is relative to the previous item, and it makes it very flexible. Okay. What is right after the return address? What is right next to the return address? The first parameter, and we call the first parameter what in the prototype? Just x. Okay. So that means x is the return address. And how long is the return address? How many bytes does it take up? 4 bytes. Okay. So x is return address plus 4. What about after x? Do we have anything after x that is useful to this particular subroutine?
Y.
We have parameter y, the second parameter. Okay. So now we have y is return. Whoops. Y is x plus 4, because x is a 32-bit integer. It takes up 4 bytes. Okay. So at this point, I have defined old EBP, return address, x and y as labels. I could have defined old EBP. Old EBP is 0. Return address is 4, x is 8, y is 12. I could have done it that way. But I do not like to do it that way because I want to show how they are relative to each other instead of using the absolute value. Okay. Are there any questions at this point? Now that I have these labels defined, and I have EBP being the frame pointer, can I change the compare instruction?
Yeah.
And how should I change the compare instruction so that it is no longer sensitive to all the additional push and pop instructions? In other words, if I put a push L here, EAX, and do a push L here, pop L here to EAX, how do I change this instruction so it is insensitive to any additional push and pops? First of all, do not use the stack pointer, right? Yep, go ahead.
EBP pointer?
We use EBP as a base register. Okay, good idea. So we changed ESP to EBP because guess what? We are not changing EBP anymore. The push and pop instructions only change ESP, but none of those two instructions will change EBP. So EBP becomes a fixed point, on the stack and say, I'm always pointing here. You can push and pop all you want, but I'm not moving. I'm still pointing to the same place. It is okay to use me as a reference point on the stack now. But instead of using 16, what should I use? I'm trying to compare why exactly.
We don't know why you're telling us.
Sorry?
I said we don't know why you're telling us.
But why is why? Why do we use why? Okay, so now that we have changed this code to this format, I can now have any number of push and pops, and it's not going to change, what this instruction. I do not need to worry about any additional push before the compare instruction, because it's not. It will change ESP, but it's not going to change the frame pointer, EBP. Are we still doing okay so far with this concept? Now let's take a look at the stack, okay? And think of it from the beginning of a function call all the way into the subroutine itself, okay? So we'll go ahead and draw a stack here. You might want to write this down because it's not captured. Okay, so let's say the frame point, the stack pointer is pointing to this point, which is not some place that I really care about. Okay. As the caller is responsible to push the parameters on the stack and then perform the call instruction. In what order? Should I push the parameter first, or should I call first? Push the parameter first, because when you call, it's no longer in your code, it will be in the subroutine. So the caller has to push the last parameter first. In other words, in this particular case, it will have to push the 0 first on the stack. How do we get something like this on the stack? The caller, in this case, can do a push L $0. That will push the 0 on the stack. So the stack pointer will now be moved to this point. Is that okay? This is my second parameter. This is our y. X is over here, so I'm going to push this one as my next one. Was it 1, 2, 3, 4, A, B, C, D, or the other way around? 1, 2, 3, 4. 1, 2, 3, 4, A, B, C, D. So this is also in the caller's code. It's push L 0x 1, 2, 3, 4, A, B, C, D. Once I have both parameters pushed on the stack, what do you think the caller has to do? Nothing, just to call the subroutine, right? So when we call the subroutine, we have the return address pushed on the stack. Is that making any sense? The push instruction is going to push the return address first, and then it will do a jump to the subroutine. So that means, from the caller's perspective, it's going to call, in this case, it's called many parameters. We doing okay so far? These three instructions are in the caller. What about the callee's perspective? Well, we are looking at the callee right now. Okay? So what is the first thing that the callee is going to do? The subroutine being called. I'm looking for another color. Yeah, black is okay. What is the first instruction the callee is going to execute? You're staring at it. Push L EBP, right? So that means the old EBP is going to be here. And this is done by push L EBP like that. But this is in the callee's perspective. That's why I used the two different colors. Blue color for the caller and black color for the callee. Are we doing okay so far? Okay. So at this point, the stack pointer, ESP, is pointing to old EBP. What is the next instruction? Right after the push L EBP, we have the move instruction. So at this point, we also make sure that EBP is pointing to exactly the same location. All right? So let's do some checking first. EBP plus 0 points to old EBP. Checks out. old EBP itself takes up 4 bytes on the stack. So the return address is EBP plus 4. Is the return address going to resolve to a constant of 4 here? What about parameter x? Plus 8, and then parameter y is plus 12. Okay. So this way, we have a symbolic constant or symbolic name or label to access all the different items on the stack. And someone's going to ask, but Tech, when do we need to access the return address specifically, and when do we need to access OEBP? The answer is no. We don't really need to access those particular items. But I would still like to use those in the definitions, just so that it is clear to us how the stack is constructed. Okay. Yep.
Could you put 12 there static?
Yeah, you can.
In place of y?
Yeah, you
and
can.
no matter how much you push and pop, the same
Right.
results.
But using this method, if I change the size of x, or if I want to insert some additional items, I don't have to redefine everything. I just have to redefine one single point, and then the entire chain will continue to work. So that's why I use the relative way of defining the constants and not just a number. But you can certainly use a number too. It serves the same purpose. Okay. So at this point, okay, right after the move LESP to EBP instruction, all the additional push and pops will simply move ESP down, 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 down. All the pops will move it back up again. All the push will move it down again. But what about EBP? Stays put. Okay, it doesn't change. And that's why EBP is called a frame pointer. Okay, it points to a fixed point of the frame of a call frame. This is what we call a call frame. Okay, so now we have. Say again.
Is there multiple frame points?
No, there's only one frame pointer because you can only be in one subroutine at a time.
Right.
So that's why we have to save OEBP, because guess what? OEBP is probably the frame pointer of your caller. Now, if you have OEBP being the frame pointer of your caller, that allows you to go back to the previous call frame, and that one in return has its own OEBP, which allows it to go backwards. So this is basically a singly linked list from the perspective of data structure of all the different call frames. And that's why GDB is able to show you the entire call history. Okay, A calls B, calls C, calls D, calls E, and by the time you get to E, you can stop execution and display the entire stack of calls and say, how did I get here? This is why. Now the other thing, we are running out of time, but there's one question that is easy to answer at this point. Where are my local variables? So let's say, many params, needs local variables. Where am I going to put those local variables? Below here. Okay. So if I want to declare any local variables, the local variables will basically go here. I just have to subtract a certain number from the stack pointer and just say that, oh, you know what, this chunk is reserved now. So I just move the stack pointer all the way down here before I execute any additional code. Then this space becomes my space for my local variables. And that pretty much completes the entire call frame, because we have parameters, we have our return address, we have our old EBP, which we need to restore when we return, and then we have our local variables. And with the local variables, what do you think would happen to the offsets? They're going to be, well, we got 0 already. We have all the things on the positive side. So the local variables are on which side of the EBP?
Negative.
Negative side, exactly. So so let's say we want to have a local variable I here. So I will have an offset of, say, -4, depending on the width of I. If I have J down here, then J would have an offset of -8, assuming it is also a 32-bit integer. So this is how things are arranged, and also this is how EBP is used to keep track of all of these things on the stack. Yep.
So you just do, for I, it would be I equals OEBP -4?
Yep. If this is how we want to do it, then we'll exactly what you said. Okay, I is old EBP -4, and then J, which is below I, is I -4. Because remember, these names are not the actual values of the variables nor the parameters. These are offsets to the parameters and the local variables. I could have named these things as offset to, but that would be a lot of typing. Since I'm lazy, I'm just going to use the name of the item that I'm trying to offset to. Okay, one last thing. Is there any difference between the way I access a parameter as opposed to the way I access a local variable if I define things like this? No. Nope, there's no difference whatsoever. Question? No? Okay. So we have just covered a lot of ground, so I strongly recommend you guys to read the notes related to this, and I will point out exactly where you need to read in the notes. We are now in topic 8. We are now talking about call frame. So that would be the link to link Zelda. But call frame is the topic now. That is what you need to do. We'll definitely talk about this again. I know I'm kind of rushing this through a little bit. So next time we'll talk about this again. And what we'll do next time is we'll set up the stack so that we can call from assembly back to C. Got it. And then assembly subroutine will call a C subroutine. Sorry? Oh, we have to and then after that.
And on.
Earlier I put away both models and plus 3. Well, 3 would be technically equal to garbage. You did plan. You're just pushing something. This time I was trying to do it over the trans garbage. But that was
I don't think what it is right now. I wouldn't know what's happening. I mean, this is perfectly okay. It's legal. It doesn't crash the program.
Probably going to ask it for the calculator.
Oh, would you shell crashes?
I was like, he helped me now. How many points it is?
For exam 2, we only cover up to pushing pop. So even call and return is not from exam 2. So you don't have to study how to push pop.
Yeah.
You do have to
Roll it right,
know how push works, how pop works. Chapter 20 is really straightforward with how to move it. Push pop and then all the way back to the flags because it goes all the time.
From black to the push pop?
Topic 3. Topic 3. So scroll up until you see topic 3. That's where you start studying.
You can do something like that.
Although, if you're shaky with the everything goes, I would definitely go back and restudy everything goes as well.
Oh, the EBIS, right?
That basically types it out sometimes.
How many questions? I would say about the same as the practice test. It depends on the complexity. Sorry? Doesn't matter. The other a practice test. But we went over the HTML practice test, in this class. That one is just a description of the questions, sample questions. No, that one doesn't work anymore because the question type that I was using before is no longer supported by Google. So that one is gone.
I know, I do that at home.
Yeah, so everywhere where the GCC is being used, so.
Yep, and the same kind of questions, I cannot guarantee how close they will be, but about the same